Thank you for joining us for the IEEE Computer Society Standards webinar series, brought to you by the Standards Activities Board. With over 225 standards that transform the way we live, work, and communicate, the IEEE Computer Society sets the standard for design automation, simulation, testing technologies, Ethernet and Wi-Fi, quality assurance processes, systems architecture, DevOps, and more. Standards deliver best practice processes for developing market-ready interoperating systems, products, and services. You can have an impact by joining one of the over 200 IEEE Computer Society Standards working groups. Participating in one of the working groups grants you access to information that reduces risks, increases proficiency, and shapes the future of the industry. Help determine what's next in computing technology. Learn more about our standard working groups at computer.org/standards.
Okay, so hello everyone. Thank you for joining us today and welcome to today's webinar from our Standards Activity Board series. And today's presentation is from the Test Technology Standard Committee. My name is Edward O, and I'm the Vice President for Standard Activities of the IEEE Computer Society. Before we get started, I would like to adjust some housekeeping items. This webinar is being recorded. You can ask any questions in the Q&A box you see on your screen. Our guest speakers will answer as many questions as possible after the end of their presentation. When submitting a question, please reference the slide. A copy of the slides and the recorded webinar will be emailed to you tentatively tomorrow. Circling back to today's presentation, as you may see from the animation, we have 18 standard committees covering different fields of interest of computer society. One of them is the Test Technology Standard Committees that promotes the development of standards in the test industry. This standard committee produces a beneficial to integrated circuit, board, and system designers, automated test equipment tube and equipment vendors, and also the developers and users of automation tubes. And as some of you may know, unlike the digital circuit, the industry actually needs a standardized way to specify the coverage of tests for analog and mixed signal circuits. The omission has led to, at best, the use of incompatible ad hoc definitions, or at worst, no quantitative consideration of analog defect coverage at all. In this webinar, we will have four standard experts that I will introduce very soon to share with us how they define the standardized analog test coverage. And this is what they will have about the propagation of the IEEE P2427 standard. So now I would like to introduce the speaker one by one. Our first speaker is Mr. Steve Sanger. Steve has been working in the mixed signal IC design, test, and DFT for over 45 years and authored about 70 papers on this topic. He has been a member, vice chair, or chair of every IEEE Standard Working Group and Conference Program Committee related to mixed signal DFT. At Siemens, he is the engineering director for mixed signal DFT, a position he has held over 25 years. Our next speaker is Jeff Willick. He is a senior fellow at AMD, where he has led the DFX strategy team for 18 years. Jeff is a member of the International Test Conference Steering Committee, served as ITC Program Chair in 2023, has served on many program committees, especially the Program Committee on the European Test Symposium, is a long-standing member of the IEEE Test Technology Standard Committee, and he is currently the editor for 3 IEEE Standard Working Groups. Prior to joining AMD, Jeff did test engineering and DFT design at Hewlett-Packard and also Agent Technologies for 22 years. And after Jeff, the third presenter is Mr. Vladimir Jigomihush. Vladimir has more than 20 years of industrial experience while being involved in mixed signal DFT, AMS test development for automation, DFT within the RTL design flow, defect simulation methodology, and AMS verification with Philips Research, NXP Semiconductors, D40 System, CRN, Cadian Design System, and Infineon. He is also one of the core members of the IEEE P2427, which is the focus of the webinar today, and also the published standard P1687.2. And our last speaker is Anthony Koyat. Anthony is the responsible for the corporate DFT at OMISAM. Until recently, he managed the test and automation methodology team for the analog and mixed signal division. He has authored more than 35 international publications and served as reviewer for multiple journals and conferences. He is the current chair of the IEEE Working Group developing the standardization of the analog default modeling and reporting. So you can see actually we have 4 speakers today who have very long and great experience in the analog industry, and they are very active standard working group contributors and leadership. So now I will give the floor to Steve to start the presentation. And for anyone who joined just late, please feel free to type any question in the Q&A box. As I mentioned, the speaker will answer the questions at the end of the presentation. Steve, you have the floor. Thank you so much.
Okay, thank you. We're going to talk about creating better analog tests, and we have contributions from multiple companies here. So the first question we might ask is, what makes a better test? How do we, what do we mean by the term better? There's various possible things it could mean. One is it could mean we have fewer coding bugs in the test. One way to achieve that would be to use a higher level language to write in and to provide more automation for checking that language and for creating the code that would run on a tester. Another way of making or defining a better test is one that achieves lower cost ICs, that each IC is cheaper, maybe because it has simpler test access to get into the chip. Instead of needing to access hundreds of pins, you might only need to access a few, or that it uses a lower cost tester, or that the test runs in less test time. Another definition of better is that it would deliver chips with a higher test yield. Meaning you get a more repeatable result, that you have more margin between the test limits and the typical measured values. And a fourth definition, which is probably the most important one, is that the test is able to deliver higher quality ICs. And we measure quality in ICs by saying, typically in measuring it in units of defective parts per million, or DPPM. And to achieve higher DPPM, we need higher coverage of the defects that can occur on the chips. Overall, we would say we need all of these things to make a better test. And the way that we're going to address that is the 2 standards that we've been working mostly on that were mentioned in the short bios. P1687.2 addresses the first items. It provides a high-level language for describing a test, and then tester companies are developing automation to go from that high-level language into the actual tester code. And that can make for higher quality tests that are easier to write. And it also describes the test access into the chip. But the focus today is more going to be on P2427, which addresses the latter items, especially how to achieve higher defect coverage to reduce defective parts per million. So we'll cover different areas. I'll provide the aspects of the industry that motivated us to draft standard. And one of the key values of the standard is the clear definitions it provides for many terms used in industry. A lot of terms, but Jeff's going to just cover some of the highlights, the most important ones. Vladimir will then give some specific examples to show where this standard can be useful, and then Anthony will draw conclusions. As always, in these presentations, these are just the opinions of the presenters and not those of IEEE or the working group. So If we look at the test time for the analog portions of chips, we see that it's a much higher test time per unit area of a chip for analog than it is for digital. And keep in mind that many chips that you might think are entirely digital might actually contain a sizable amount of analog. A PLL is the most frequent example, which is actually analog in nature, but has a digital input and output. And for chips that are mostly analog, they tend to be very high volume chips, and typically greater than 10 million units per year. And so considering that test time can be anywhere between 2 and 8 cents, US cents a second, you can see that the costs are quite a lot. And if we can reduce test time by a second or so, that can add up to a sizable amount, not to mention the impact of lower quality. And the time to develop analog tests can be significantly longer than for digital tests. And that's mostly because there's much less, or in many cases, no automation for having designed for test methods inserted on chips, or for developing the test, describing the test, or providing test access. And if we want to develop those new methods, we need ways to compare them that are very objective so that we can say this design for test method is better than that one, or this test is better than that one. And so for many, many years, we've had no industry agreed way to estimate the quality of chips before we actually ship them. It's relatively easy after we ship them. We ship millions of the devices, and we see how many defective devices are returned by customers. But clearly that's a very expensive and time-consuming way to go about it. So we want to focus on what we can do before the chips are shipped. A brief history of how this standard came about. 10 years ago at the European Test Symposium, we had a special session that was addressing analog test and DFT and the state of the art. And we realized that the state of the art for analog was about 30 years behind that for digital circuitry. And so 6 of the presenters from the session there decided to start meeting weekly to see if we could address those fundamental reasons. At the end of a few years, we were working on a rough draft of a document which we decided could be the analog test access and for analog defect. So in 2017, we formed a formal IEEE study group, invited people from industry to join, and a lot of people did join. We had meetings with 70 members, and at the end of about 6 months, there was unanimous agreement amongst those people to form 2 working groups, the 1687.2 and 2427. So then a year later, in the 2427 group, we had about 45 members, many of whom were also in the 1687.2 group. And those members came from over 20 different institutions, from chip design companies, from tester companies, from EDA companies, and private consultants. And then went to first ballot a couple of years ago, and we're in second ballot now. So in terms of the tended to address, imagine that we've got an analog that maybe its net list has a couple thousand transistors and a bunch of capacitors and resistors. And we have 2 different tests where we'd really like to use this 2 millisecond structural test. On the other hand, we feel more comfortable with a 200 millisecond specification test. So doing a defect simulation would allow us to see, is the structural test as good as the specification test? Is it a better test? Another more common example is where I have one test, regardless of what kind of test it is, and I'm trying to decide, do I need to run that test at multiple temperatures, or can I just run it more conveniently at one temperature? If they have to run it at 2 temperatures, that's going to be, in effect, twice the test time of running only 1 temperature. So, well, how many potential defects are there in a circuit of this size? In theory, it can be almost infinite. I could have a short circuit between any 2 nodes of the circuit. I could have, in terms of parametric defects, there's a continuum of values of each capacitance and resistance and transistor thresholds and so on. So there's a large number of defects I could consider. But given that it takes a long time to simulate each defect, one at a time, and we've not seen any technology for simulating multiple analog defects at a time. So the time to simulate each defect could be from a few minutes to several days. In the case of some PLLs and SerDes lanes, it can be many days of simulation per defect. So even running on many computers in parallel, it can take a long time. And that would just be for the typical process. In analog, designers often add extra transistors to make the circuit meet its specifications at the process corners. And therefore, defects in those transistors might only be detected if you simulate those process corners. What we have found in answering this next question, how many representative defects do we need to actually simulate? We've found that it's usually practical to simulate fewer than 500 if they are randomly selected from the circuit that we're considering. So that makes it a much more manageable problem. We just need to clearly define what the defects are. And so now we'll go on to Jeff to cover some key definitions.
Thank you, Steve. And I'll pick up on Steve's excellent motivation by starting with that 30-year gap that he talked about with digital. You may know several of these terms from digital design. We talk about tests and faults and the collection of faults making a fault universe, and the percentage of detected tests of that fault universe representing a fault coverage, and the testable faults defining a test coverage. Well, as we looked at it, it turns out for analog circuits, the problem is a little bit more interesting than just this. So we changed the terms a little bit, and you'll notice the really big one is changing faults to defects. What is the purpose of that? Well, really think about a fault as an abstraction of a defect. And to do analog coverage analysis properly, you really need a more detailed view than the logical abstraction that's possible in digital circuits. So we had our work cut out for us, and where we started with is let's redefine the terms and make sure that we're dealing with the right quantities. So let me take a quick pass at explaining those. But what you're going to see is overall creating better analog tests is going to require detailed attention to these defects. That is one of the underlying principles of this standard. So let's define those 5 terms. A test, really not much difference here than you had in digital. A test is stimulus and expected response. The subtlety that we add in an analog circuit is that analog circuits are much more susceptible to process variations than digital. And therefore, we have to say a test passes a defect-free circuit that has process variations within an acceptable range. And ideally, that's the acceptable range the designer used when he created the circuit. A defect is an unexpected physical change of a circuit element, and a circuit element is a resistor, capacitor, inductor, transistor, diode, or the wiring in between those circuit elements. We left that somewhat vague. There can be lots of things that cause defects. And as you'll see, we've lumped these into 3 larger categories that I'll talk about next. And that's in the defect universe. So what comprises the defect universe? As Steve mentioned, there's almost an infinite number of things that can go wrong with a circuit, but we want to make this a very crisp definition. So we looked at what are the reasonably likely defects. And in this standard, we define them as shorts, which are unintended connections between nodes, opens, which are unintended disconnection on a single wire, And then parametric defects, and you notice I put that one in square brackets. Those are optional. The standard mandates that we determine coverage of shorts and opens. You can also do parametric models as well, but it's not mandated. And these are derived, the reasonably likely defects are derived from the circuit's net list. And that could be either from a schematic or a layout net list, depending on what you have. Now, the key items we're producing with all this information are defect coverage and detectable defect coverage. So defect coverage is fairly straightforward. What percentage of defects did you detect from the defect universe? And when we say detect, that means the test that we defined earlier fails its expected response in the presence of a defect. And you'll notice this definition starts with the word weighted. We very much take into account the likelihood of a defect. And there are several methods for determining that. It's up to the user. We give recommendations and expect that the user must declare what weighting he used. The simplest kind that I'll show later in an example is weight all defects equally likely. That's what the digital world often does and has done for decades. It's not what we recommend. We recommended weighting based on the total critical area in the layout. That's more detail than we need to get into for today's webinar, but that's the level of detail that we go into in the standard. And finally, probably the most useful definition is detectable defect coverage. What that does, it's the same as defect coverage, except that it excludes undetectable defects. Why is that important? Some defects, no test can be written to detect them, so we exclude those. And what that lets you do is have a goal, your coverage goal being 100%. So ultimately, that's what we want to see is analog tests that can achieve 100% coverage of all detectable defects. So what does all this mean? It's a nice set of words, but let's actually look at an example. I'm actually going to start with a digital example and to show you the importance of being detailed instead of abstract. So here's a 3-input exclusive OR gate. In the digital world, that would have 8 faults stuck at 0 and stuck at 1 on each of A, B, C, and Q, the ports. To detect those 8 stuck at faults, you only need 2 patterns, all zeros, which produces a 0 on the output, and all ones on the input, which produces 1 on the output. So all of those stuck at faults presumably would be detected by this. Now, even in the digital world, we can do better than this. Let's take a look at that same example, but in more detail. Let's actually look at the transistor implementation. This is just one possible implementation of that gate. There are a few others. But right away, you'll see 8 parallel stacks of transistors, 4 to the power supply up on the P transistors and 4 on the N transistors down. And it's pretty intuitive. Well, gee, I have to look for defects in each one of those stacks when that stack is operating individually, turn all the other stacks off. I think I'm going to need all 8 patterns. And indeed, all 2 to the 3rd possible input combinations are necessary to fully test that group of transistors. So even in a digital world, looking at a more detailed level gives you a far better picture of the essential tests to achieve high coverage. And that was very motivating for us. The digital world has been moving in this direction in the last decade, and the analog world needs to start here. So that was very much the starting point for our standard. So what does it mean to add defects to that particular digital example? Well, we're going to consider shorts and opens and parametric defects. And I've just illustrated a few of these. The opens I indicate with the little yellow circles on a connection between 2 components. The shorts are the little curved lines that would join 2 different nodes together. Over on the lower left, you'll see one that joins nodes in the 2 different stacks. All the other ones join 2 different terminals of a given transistor. So there are some very well-defined ways that you can know exactly where to inject these defects, and that defines our fault universe. On the lower right, I've shown a parametric defect on 1 transistor. And if we count that up and say, hey, I was going to do that on every transistor, I'm going to put opens on all the IOs, and I'm going to put opens in the middle of every node in a stack, and I'm going to put shorts between every terminal of a terminal pair of a transistor, and I'm going to put in shorts between corresponding nodes from one stack to the other. And I'm going to put in a parametric defect on every transistor. This circuit, instead of having 8 faults, would actually have 178 defects. Now, that's a very well-defined fault universe. And I can do it by looking at, in this case, the schematic of the circuit. Now, I could probably do a better job on what the actual shorts are from wire to wire by looking at a layout. And we have in our standard both possibilities available to us. Okay, so now let's look at this in an analog context. So here's a simple analog circuit, just an op-amp, small enough that we could, instead of sampling, say, 500 faults, this has fewer than 500 defects. Instead of putting in a sample, we can put every defect in this one at a time. And I'll show you what that looks like. So here's that same circuit with all the defects injected. And as the title says, and as Steve mentioned, we only do these one at a time and then iterate through to see, does this test change its output in terms of or what it does in a defective circuit compared to a defect-free circuit. So this circuit has 62 opens, the little circles. It has 48 shorts, the little curvy lines, and it has 20 active devices, transistors, diodes, and a capacitor. And if all the weights were the same, I can easily tally my coverage, which I'll do on the next slide. But this is a simple example of how to definitively, unambiguously define what the fault universe is and where those faults are. Then we run the tests in an analog fault simulator, and what we end up with is a coverage. And here's an example. Now the figure only has the defects that are left that were undetected by a particular test. The particular test, and thanks to Steve for this example, he actually ran this through the simulator, with a 1 megahertz sine wave being applied at the inputs of the op-amp, and seeing, did the output change in a measurable way? Many of the defects were detected. And down in the lower right of this figure, we separately require reporting of what was the open coverage, what was the short coverage, and what was the parametric coverage. And those came out to 90, 87, and 65, respectively. So now, as an analog designer, you've got a very, very good, crisp definition of how effective your test was and what defects were covered and uncovered. So if you wanted to achieve higher quality, you would have to write some additional tests to pick up the remaining defects that are shown in this picture. And that's the beauty of this standard. It tells you exactly in a detailed fashion, because of our crisp definitions of the fault model and the fault universe and what a detection comprises, of exactly how to do that. So hopefully with that set of definitions, Vladimir can help you get motivated on the next set of examples. And then our bottom line here is what gets measured gets fixed. So defining these metrics is really the key to writing those better tests. Okay, I'll hand it over to Vladimir.
Yes. So I will continue now with showing, how the standards could work in practice, and starting with recommended defect models. So as Jeff mentioned, we are doing the analog defect simulation campaign, so that is a circuit simulation, and obviously we need to capture the defects that occur in the layout and the silicon into the model that we can use during the circuit simulation. So for short, open, and parametric defects, we have, after some debate, the standard consortium concluded that we would not mandate but recommend these defect models to leave certain flexibility there, of course, which may vary of the technology, the fab, and the statistics related to the field failures. So for shorts, we would recommend a resistor, so for example, 100 ohm resistor, to be connected between these terminals where the short would occur according to this algorithmically described defect universe. And we also have an option to allow this defect for the higher frequencies, where we would recommend to connect in series an inductor to the resistor. So this resistive short has a small value. For the opens, so as Jeff explained, they occur on a single net. And for that, we would have typically a resistor with a large value, and also for the higher frequencies. It would be we also recommend to connect a capacitor in parallel between these open wires. Well, the gate of the transistor did require a bit more careful and meticulous approach, because the behavior of such defect, or the open gate defect, it's been observed that it exhibits a different behavior than just an ordinary open on the other terminals of the transistor or on the other devices. So for that, we have a particular defect model, which actually can be shown here, that it could be either complete open or a voltage divider, where this divider, the resistive divider, connects between the two other terminals of the transistor, between drain and source. Parametric defects, well, there were approaches in the literature in the past that looked into the maximum deviation from the specified sigma, 3 sigma, for example. However, the behavior of such defect would depend on circuit sensitivity, so we have taken other approach to introduce some sort of a deviation factor to PDK, to process design kit, and here we recommend that this deviation factor is 2 times worse than maximum acceptable value specified in process design kit. So here I will also show now an example of a defect coverage summary, which is another collateral of the standard, which also came with a number of rules and recommendations to allow fair comparison of reported coverages, and also relying or taking into account the definitions and the terms that Jeff just described. So here is just a small example of a basic actually report summary or executive summary report for circuits. Let's say that it is an ADC P2427 benchmark, where you would see that here we are mandating the coverage of shorts and opens. Parametric is not mandatory. So here I'm showing shorts and opens only, and their opens are then also split into open on gates and others, because defect model for gates is different. So then it would be also reported appropriately here in this table. Here we see the number of simulated defects. So again, this is not exhaustive campaign, but based on the sampling. Sampling is also reported in this column, so sampling algorithm. So likelihood weighted constrained random sampling, that seemed to be also the best actually approach. Well, again, there is no mandatory sampling, but it needs the algorithm used for sampling must be reported. And here you can see, for example, here this is only defect coverage, but obviously we also recommend to report detectable defect coverage, which is more useful metric for DPPM, as you will hear from the next presenter. And then it can, of course, happen that during simulation that the behavior of a defect could cause, for example, convergence issues or simulation, or the oscillation during the simulation, meaning that the simulation never ends. And then the status of such defect is reported as unknown and is also taken appropriately into the coverage calculation. The sampling also comes with a confidence interval. Obviously, that depends on the number of samples and also the achieved coverage. And again, that this confidence interval is a mandatory report. Also the corner where the defect simulation campaign has been done, and a list of applied recommendations, again, to apply their comparison, applied recommendations of the all normative part of the standard. Also, a list of tests or just a short descriptions. They understood that the test itself, the detailed description of the test, may also incur into the proprietary part of the company. So here we are only mandating that at least a short description of the tests that were applied to achieve this given coverage is also reported. So here are the examples where P2427 can help. So obviously in the IP delivery, where a company, associate integrator, is considering to buy IPs from different vendors, and then if one of the criteria is quality of test, then P2427 can offer also a fair comparison of the achieved coverage and all basically tests and all recommendations that were followed to achieve such coverage. Then it also enables university researchers to benchmark their work and then also claim that their approach is better than the others. Again, fairly comparing the results of their approach using the P2427 reports. The standard also may guide DFT engineers to define the targets for simulation, defect simulation, instead of, well, I would say some arbitrarily eliminating part of the circuits from the campaign. And it also helps with the test escape analysis. So it could point to incomplete manufacturing test set or another failure mode, or potentially also incorrect simulation test bench. So in any case, this would require further analysis for any of these situations. So far we talked about manufacturing test. However, this standard is also useful for functional safety, and because defect injection can also be done at time that is greater than 0, so for in situ tests, and or also to check the safety mechanisms, and it can be used to provide metrics for ISO 26262. So in the other words, also for diagnostic coverage and for ASIL qualification. With this, I would like to move to the next presenter.
Thank you, Vladimir. So Steve, Jeff, and Vladimir have addressed multiple aspects of this upcoming standard from the IEEE, the P2427. In multiple ways, they've shown you the contribution that this standard will bring to the industry. It's not so much that we expect you to be convinced right away, but we hope you have now a better understanding of the impact that will be made by 2427 on the industry. The bottom line will be impacted, and we want to emphasize these 3 points here. I'll start here with the 2427 will drive, or will be a key component to drive higher quality. It will be an essential tool or layer of standardization to drive for higher defect coverages, which therefore will result in fewer defective parts at the customer, fewer defective parts per million DPPM. The second point we want to highlight is that P2427 will have an essential role to play to drive the test cost to a lower point. It will be a tool to be used to explore tests, compare tests, and find a test that use less time, or possibly a simpler, cheaper AT configuration. Last but not least, this standardization, the standard is bringing, it will, by the standardization layer that it brings, it will increase the repeatability of the experiments being made. It will facilitate the analysis by the engineer, and it will bring some DFT automation. The first point I was citing, higher quality. It could be at product level, it could be at IP level. There are multiple configuration or situation to be addressed. You are either integrating a product or you are providing a product to a customer, P2427 is bringing deliverables where you have clear numbers, defect coverage, detectable defect coverage that you can show to your customer, showing that the method that you have designed is reaching this 98% coverage, like you were doing in the digital, and therefore providing good quality data being researched. Could be that you're integrating an IP from an IP vendor, and when your IP vendor is providing you that IP that you have to integrate in your chip, when you have this integration guide and the test that he's proposing, you also get this now quantified number, this 95% detectable defect coverage, and you know that you will be able to, with that method, to provide good quality to your own customers. The second one, second point we were emphasizing, so driving test cost, test time down. In the past, when you were analyzing an IP, you could definitely measure the test cost, the test time and test cost that a method would be taking. And now what 2427 is bringing you is a standard way, a repeatable way to measure the quality, the defect coverage that a test is how it is impacting your quality. So when you have multiple test methods, you used to have the test cost, test time, and now you also have a clear quantification of the quality, and you can make comparison to it. You probably want a high defect coverage, detectable defect coverage at the lowest time. It's not always possible, but you can compare method 1 to method 2, method 3, and make the best selection for your profile that you are seeking. Now we have been talking about standardization for now about 45 minutes. Where are we with IEEE 2427? Where are we in the process? Steve told you it all started 10 years ago. There is a lot of effort that went into this standard, a lot of writing from the working group to produce that document. In terms of process and standardization, the group went for first round of balloting 2 years ago. So in June 2022, the group went for the first ballot, gathered a ballot of 38 experts in the industry. Actually, it was an open call. They had a response rate of 76%, so meaning 24% did not submit the ballot in that round. And the approval rate was 42%, which is actually an okay number, considering that we went very early in this balloting process with 2427, since we knew we would get quite some comments that we would need to process and we would need to iterate at least once. We got 967 plus 2 years to process every single comment and accept, revise, or reject some comments. And a couple of weeks back, we started what we call the recirculations. We go back to these 38 balloters to seek their approval. And by the statistics I see today on the dashboard, we are very confident that we'll be successful in reaching this 75% approval rate. That's what you need to get to go for publication. I'm confident we will get to the 75% in the next week. And then we are looking at a publication for 2025 Q1. And then that standard will be impacting the industry like we have explained to you today. And thank you very much for your attention.
Okay, it's great. Thank you so much, Steve, Jeff, Radamira, and Anthony, for your great overview of the latest standard development related to the NNIC testing, especially related to the P2427 standard. As you may see from the chat box, actually, there are quite a number of questions already. So now I will ask each of you to see who may be willing to answer our audience question. The first one, actually, as you may see from the attendance check, the audience asks, is less than 500 tests for analog insemination or post-silicon test? who may want to answer this question?
Just looking to see where that's in writing.
In the attendant check. In the attendant, not the Q&A.
I see,
yeah, they now ask all the question in the attendant check. So please, the first question is less than 500 tests for analog in the simulation or post-silicon test?
Hey, I suspect that it's a slightly misworded question. That the number 500, came up in Steve's talk as the sample count for defects, not tests. The example I showed, there was one test, just a sine wave test, and we injected all the defects because that circuit was so small. But typically in a larger analog circuit, no matter how many tests there are, you want to choose a random sample of around 500 defects to inject. And then that is only a simulation approach. When you're at post-silicon, obviously, you're not simulating anything, you're not injecting any defects, you're testing real product. And you're going to use that same test on post-silicon. So the primary purpose of this standard is to quantify the pre-silicon simulation. What is the coverage of a test likely to be? And that's where the sampling of 500 defects makes sense. So I hope that clarifies that. And if I'm answering a different question than you meant to ask it again in the chat, and we'll pick that up.
Okay. Now that I see the exact wording of it, yeah. So you just add as many tests as you need to get the defect coverage you need. There's no requirement on number of tests, but that comment is about the number of defects. And the short answer is along the lines of what Jeff said, that regardless, you only need to take a random sample of fewer than 500 defects to do the simulations of whatever number of tests you're planning to do to get an accurate estimate of what the true defect coverage is.
Okay, great.
See, somebody else is going to ask, why 500? Why not 200? Why not 1,000? And it has to do with the confidence interval that you are claiming, so that to get an accurate value for the coverage, 500 gets you within, I forget what the number is, some percentage of the accurate. If you want a tighter confidence interval, then you select more defects to run. And of course, that costs you more runtime and all that. 500 is a decent number to get you good enough accuracy and reasonable runtime.
Okay, great. Actually, the audience actually have their follow-up questions. So maybe you can go down a little bit to their attendance check. Actually, the audience asked two more questions. That, for example, which tube is used for disseminations? And then can you give an example of the parametric defect?
So in terms of which tool is used, this standard is independent of tools. You would use the simulator that you normally use to do verification of functionality in simulation. So the standard, in fact, recommends using the same level of accuracy as was needed for regular verification of functional design in simulation. And as an example of a parametric defect, if you were talking about a resistor, then a variation in that nominal resistance would be a parametric defect. In the case of a transistor, you might choose to simultaneously vary the width to length ratio and the threshold of the transistor. In other words, 3 different parameters to reflect what you might say is a 4 sigma or 5 sigma variation in that combination of parameters. So it can either be single principal parameters or it can be multiple parameters varying at the same time.
Coming back on the tool,
it's important to point out that
the standard is independent of the tool. No, I just want to come back on the tooling. It's like the standard is definitely independent of the tool being used, but I just want to point out that in terms of readiness, each of the 3 major EDA companies is offering a solution. So it's not like something abstract. If you go and talk to your EDA provider, he will point you to a definite tool to implement 2427. Go ahead, Jeff.
I was going to mention two things. So following on what you just said, Anthony, just in case there are any digital folks in here, like me, I'm a digital guy amongst a bunch of very smart analog folks. Just to name this, and this is not an RTL simulator or a gate simulator. This is a circuit level simulator like SPICE. And yes, all three major vendors have SPICE tools, and I think they've all adapted them to be able to handle single defect injections. So just to be very clear about that. Then the other thing I was going to point out, as Steve mentioned, parametric faults is a big category. I think the latest SPICE models for transistors have something like 800 parameters, and you could pick any of those and say, I want to make this parameter out of spec by a certain amount relative to the PDK allowable variation. So that's why the standard didn't say, here are the parameters you should use. You can use whatever makes sense. If your particular process is out of control on one parameter, you might be very interested to see how your tests cover that. And the standard, all the definitions are built such that you can put whatever parameter you want. Or combination of parameters you want. It's very open-ended on how to do that. And so I give high credit to the working group for building what I think is a very future-proof standard. As IC processes change and their dominant defect mechanisms may change, I think the standard has done a good job of being able to say, fine, we can account for that.
Great. So now we go back to the second question, because the first audience asked 3 questions, crossing the second question. The second question is from Ray. The audience asked, should the P2427 standard evolve to incorporate predefined weights derived from PDK rules to enhance defect coordination and prediction accuracy? So maybe he's talking about future standard already. So, but what is your opinions?
Yeah, so we definitely left the weights as an open-ended thing. We did not make any specific requirements on what the weights should be. We made some recommendations that it should be based on critical individual elements, the dimensions of those critical areas. For example, the spacing between interconnect, or the length of a transistor, the width of a transistor, recommended that it be based on those, but we gave no specific weights. That would be up for individual people to decide what that weighting is. What we did mandate is that you must explain the algorithm you used for weighting the defects.
Great. Any further clarification from any of the speaker? Okay, hearing none, then we have 2 more questions, two more set of questions from 2 more audience. The second last question is, the second last audience, you can see they asked 2 questions. What is the best way to inject a defect in order to detect a parametric defect? And another follow-up question from the audience is, how to obtain parametric defect coverage?
Yeah, that's an interesting one. So in terms of injecting it, that's relatively easy because the typical case, you will inject a single parametric defect. In other words, a single circuit element with a variation in it. Not, in other words, like a Monte Carlo thing, or putting parametric defects or parametric variations in lots of elements, a single element. The reason the parametric defect coverage will always be lower than it is. So in practice, what you find is that it's far more important to focus on the shorts and opens initially, because in many cases, you'll find the coverage of shorts and opens is only in the mid 80s percent, and you'll want to get it up to mid 90s. So that's going to be a fair bit of work to make the tests get up there. And once you get to, let's say, 95% coverage of shorts and opens, you'll find that the parametric defect coverage of single parameter variations in individual elements, that coverage will typically be 10 to 20% lower than the coverage of shorts and opens, and therefore much more debatable as to how meaningful that is.
Okay, great. Then we have more question come. But anyway, Timothy question is how is the fit weighting derived? So you can see the question from Timothy. How is that weighting derived? Yeah.
Right. So just the defect weighting can be, for example, derived based on a schematic and based on the dimensions of the circuit elements used there, but it can also be based on the layout and the total critical area and even take into account the defect distribution size. But here, what is very important is that even if the defect weighting is derived from the layout, that doesn't mean that the defect simulation campaign needs layout extracted netlist to run. No, these defects weighting will be based on the layout, but they can still be used in the schematics. So the defect simulation campaign itself can run at the schematic level. Now, just like what Steve already mentioned, the calculation of the weights and association per defect will have to be reported. I mean, must be reported, but we do not mandate particular algorithm.
Okay, great. Oh, actually, the good thing is people get excited by the Q&A and keep asking questions now. The bad thing is that we have a time limit. So we can answer 2 more questions before we conclude. Okay, so Josh have a question is like, does a single parametric defect encompass the entire spectrum of out-of-spec values for a defect at that position, or does it pick a single out-of-spec value? I think Anthony answered in the chat box is pick a single value, right?
Already answered this now.
Okay, no problem. Okay, then the next question is, should evaluating test methods and resulting coverage be part of a standard development flow or be part of the quality improvement? So any speaker would like to answer this question about the test method evaluation and the result coverage? Should it be standardized or it is just at the end, the QE, the quality improvement?
I think it can be used in both ways. Obviously, we would recommend that during the development of the project, as you're creating tests and driving toward tape out and first silicon and all that, you should have a very good handle on your defect coverage. And if it's low, you should be adding more tests. If you've gone to production and you've got a defect problem and you need to improve your quality, it's late to get started, but this approach that we're talking about in our standard is going to help you, because it will, if you simulate your existing tests and find out where they miss coverage, you'll know what to go add. So it can be used in either way. Obviously, it's in most companies' best interest to do this sooner rather than later.
Okay, great. Anyone want, any guest speaker want to follow up also? Sorry, I interrupt you.
Yeah, I was just going to say it's not suitable for defect diagnosis, which might be considered part of failure analysis. Having these defect models does not help you diagnose defects. That's a completely different task. So it's more, as Jeff said, that you would use it up front for assessing the coverage of tests and making that as high as possible.
Okay, great. So actually, we are already at the end of the presentation. I understand there's still questions. The most possible way is for those audience who may be interested, please visit the P2427 website, and at the end you will find the speaker information and email address. You can follow up with them. And also another alternative is to participate in the Test Technology Standard Committee to have the ongoing discussion and contribution, and it is the good way to do so. But once again, I would like to express my sincere thanks again to Steve, Jeff, Fedemira, and Anthony for joining us today and for sharing what is going on the world of the analog IC testing. especially related to the latest development of the job standard P2427 that will be published very soon. A very quick programming notes to all. On November 12th, we will host another standard webinar, which is from our Functional Safety Standard Committee. Our expert from the Functional Safety Standard Committee will present a webinar, Control-Oriented System Safety Analysis, that they will talk about the objective and use case of the analysis and how the analysis fit with the functional safety and system engineering. And as I mentioned at the very beginning, this webinar is already recorded, and the slides that will be shared with you together with the recorded webinar tentatively tomorrow by our society staff. Once again, I would like to thank all of our guest speakers and also our society staff and all of you for joining the call and for a lively Q&A discussion. If you celebrate Halloween, happy Halloween, and then thank you so much. And please remember, if you are interested, join the Technology Standard Committee to discuss and contribute. And now is the end of the presentation. Thank you so much all. Bye now.
Thank you. Bye-bye.